student must hold each end of the spring coil that must be stretched 5 meters apart. One student will send a pulse through the coil by flicking his or her wrist, and another student will time how long that pulse takes to travel to the other student and back. So for part A, we recorded the time for the pulse to go forward and back, and we got the time of 1.19 seconds. Then we tried to find the velocity, which is distance over time. And for distance, we put in 10 meters because that's the distance for the pulse to go forward and back, and the whole spring is 5 meters, then it will be 5 times 2, which is 10 meters. Then I put it over the time, which is 1.19 seconds, and I got the velocity of 8.4 meters per second.
For part B of this experiment, instead of sending a quick pulse through the coil, the student will make standing waves by shaking the coil up and down. With this experiment, we are trying to find the frequency of the waves by timing how long it takes for 10 vibrations to be complete.
So the total time for 10 vibrations is 5.95 seconds, so we use that to calculate the frequency, which is 1.68 Hertz. And then we know that the frequency, we could plug it into right here. So we have to find the wavelength, which is 5 meters because there's 2 segments, and 2 segments make up 1 wavelength. So we plug that in, and then the velocity we found is 8.4 meters per second.
So the velocities of both part A and part B are the same because we used the same coil for both experiments and because the distance between the two students were the same.
How it works. A Clampy plate consists of a flat sheet of metal, usually circular or square, mounted on a central stalk to a sturdy base. When the plate is oscillating in a particular mode of vibration, the nodes and antinodes set up form a complex but symmetrical pattern over its surface. The position of these nodes and antinodes can be seen by sprinkling sand upon the plates. The sand will vibrate away from the antinodes and gather at the nodes.